Hi guys, today we're going to learn about the convergence and divergence of series. Specifically today we're going to talk about the direct comparison test and the limit comparison test. Let's start with direct comparison test. If we have that a sub n is greater or equal than 0 and b sub n is greater or equal than 0, we have two conditions. If the series from n equals 1 to infinity of b sub n converges, and we have that 0 is less or equal than a sub n, less or equal than b sub n, we can say that the series from n equals 1 to infinity of a sub n converges. Okay? On the other hand, you might have that the series from 1 to infinity of a sub n diverges, and that 0 is less or equal than a sub n, less or equal than b sub n. Then what you can conclude is that b sub n, the series, is going to diverge. Okay? So what's the business here? Here, this is going to be the one that you are comparing it to. If this one converges, since it's bigger, then the one that you want is going to converge because it's smaller. On the other hand, over here you have that the one that you are comparing it to diverges. You can conclude if that one is smaller than the original. Okay, so you're going to see it in examples right now. Okay, so you can see that here you have the first example. It says determine whether the following series converges or diverges. Okay, so here we have from 1 to infinity of 1 over n cubed plus 1. Okay, so you're going to tell me how in the world I'm going to know what I need to compare it to. So here what you do is, it's not a p series, it's not a geometric series. When you do the nth term test for divergence, this one is going to be give you 0, which is going to be inconclusive. Therefore we need to, and also the integral is not going to be a fun thing to integrate, so the integral test would not be a good option here. So the best shot is to spot this part. Okay, so you are going to compare, okay, you are going to compare this series to the series when n equals 1 to infinity of 1 over n cubed. This one is a well-known series. We know that this is a p series. Moreover, you know that this p series, the p is equal to 3, which is greater than 1. Okay, therefore you know that this series, okay, converges, okay, by a p series test. Okay, so that's what we know. Now the question is, we know that this converges. Now what? Now we're going to use one of these two conditions. Okay, so since it converges, I'm going to use this one. I want this guy to be bigger than this one. Okay, so if this converges, then this one must converge. Okay, so you are going to ask yourself, is this true? Ask yourself, is it true? It is true. Okay, it is true. Therefore, since this is true, okay, we can conclude that since the one that we're comparing, 1 over n cubed, converges, okay, we know that the original that we have, n equals 1 to infinity of 1 over n cubed plus 1, converges by direct, okay, comparison test. Okay, so that would be enough. Okay, so you have this, you have here concluding that the one that you're comparing it to converges. So that's pretty much it for direct comparison. Okay, so let's look at another example. Over here what you have is that you have the summation from n equals 1 to infinity of 1 over 3 to the power of n plus 2. Okay, so what are you going to compare it to? Well, here again, it's not a p series, it's not a geometric series. The nth term test for divergence doesn't work. The integral test would not be fun. So the only shot that you have is direct comparison. Okay, so again, you spot that. Okay, so you are going to compare, okay, to the series that starts at 1 and goes to infinity of 1 over 3 to the power of n, which you know that this is going to be a geometric series. Look at that, 1 over 3 to the power of n. Okay, so this is a geometric series. Okay, and you can see that the common ratio is 1/3, which is less than 1. Okay, so what's the business? Converges, okay, this one, by geometric series test. Okay, now you need to compare. This one converges, therefore it's pretty similar to the previous one. Okay, since this converges, you want this one to be bigger than this one. Okay, so you're going to be like, is this true? Ask yourself, is it true? It is, because we know that if the denominator is bigger than and the numerators are the same, this is going to be smaller. Okay, so check. Okay, so since we have that the summation from n equals 1 to infinity of 1 over this, okay, converges. Okay, we know, what do you know? We know that, okay, the summation from n equals 1 to infinity of 1 over 3 power n plus 2, okay, converges, okay, by direct, okay, comparison test. Okay, and that's it for this example. Isn't that simple? Now you're going to tell me, how about if it's not the case? Well, if that's not the case, let's look at the following example. The following example over here, do you agree that again you are like, okay, I'm going to do a p-series test, doesn't work, geometric series test, doesn't work, n-term test for divergence, doesn't work, the integral test would be a mess with this exponent, right, with this term that we have over here, so watch out. Okay, so you're like, okay, I know that I'm going to, following the same idea, the same trend, I'm going to compare it to that one, right? And I would be like, yes, you're right. Okay, so compare to, and you are going to do the summation from n equals 4, why 4? Because that's the one that we have over here, but doesn't matter, treat it the same. Okay, so you have 1 over root n. You know that this one, pretty much the exponent is a 1/2. Okay, so you're going to compare it to that, so you know that this is a p-series. Okay, moreover, you know that the p of this p-series is 1/2. P-series with a p less than 1, you know that this guy is going to be diverges, okay, by p-series test, right? Now, what's the business here? Since this guy diverges, we know that this diverges. We want this to be smaller than this. Why? Because if the big one diverges, I don't know anything about the small one. But if the small one, that it's this one, diverges, I can conclude from a bigger set. Okay? So you ask yourself, is this true in this case? Okay? Question mark. Yeah, it's true, because we have the root n minus 1 here, okay, which the denominator is smaller, meaning the number, the overall number, it's bigger. Okay, so check mark. Okay, so we have that since, okay, we have the summation from n equals 4 to infinity of 1 over root n, okay, diverges. Okay, what do you know? We know, okay, that the series from n equals 4 to infinity of 1 over root n minus 1, okay, diverges, okay, by direct, okay, comparison test. Okay, and that's it for this one. Okay, so remember some pointers here. You need to find a meaningful series to compare it to. Obviously, it's going to be a p-series or a geometric series in general. Depending if it diverges or converges, you are going to select one of the conditions that we have over here. Okay, so that is pretty much it for the direct comparison test. The next test that we have is the limit comparison test. Suppose that a sub n is greater than 0, b sub n is greater than 0, and we have that the limit when n approaches to infinity of a sub n divided by b sub n is equal to L. You're going to tell me which one is which. Well, this is the original, okay, the one that we're looking for. okay, original, and this is the one that we're looking that we're comparing it to, okay. Suppose that limit gives you a number or something. Let's call it L. L must be finite and positive so you can conclude, okay. By finite, it means it cannot be infinity, it cannot be negative infinity, it cannot be negative number, okay. Then the two series that you have, the summation from n equals 1 to infinity of a sub n and the summation from n equals 1 to infinity of b sub n, either they are going to both converge or diverge, but both of them will have the same conclusion, okay. So determine whether the following converge or diverge. You have this one, okay. So we have the summation from n equals 1 to infinity, and you have n power 4 plus 10 divided by 4 times n power 5 minus n cubed plus 7. Okay, so what's the business here? You are like, okay, so I cannot apply the geometric series test, the p-series test, the n-term test for divergence. Fail. Then you're like, maybe the integral test works. Well, here it wouldn't be okay, but with this, if you take the derivative of this one, do you agree that that's a negative 3n squared that I don't see here? So I'm not even going to deal with the integral because it would be quite tedious. We'll call it that. So you can see that from that, we cannot apply any other test. You're going to tell me, well, we can do direct comparison. Well, yeah, let's start thinking about that. Compare this to what? Compare to, I would be comparing it to, what do you think? You are like, oh, this is not straight cut. You are right. Okay, so the problem that you have here is that you have power 4, okay, at the top, okay, degree 4 and degree 5 in the denominator. So honestly, I would compare it to n power 4 divided by n power 5. That's going to give you that it's 1 over n, okay? So you can see that over here, I'm going to compare it to pretty much 1 over n, that it's a harmonic series. That's a p-series that I know a lot of information about, okay? So this is a p-series, okay, with p equals 1. So you know that this is a harmonic series, okay? So what do you know about the harmonic series? Okay, we know that this guy diverges, okay, by p-series test or because it's a harmonic series, okay, either would fly, okay. So we know that one for sure diverges. Now you're going to tell me, oh, okay, so let's use direct comparison. Are you going to compare this monstrosity with this? That's a lot of algebra, okay? So what you're going to do here is okay, I know that this diverges for sure, so let's use the limit comparison, okay? So the limit comparison, you don't need to compare it like the other one bigger than the other. You just do the comparison directly, okay? So you put the original at the top, okay, as the numerator, okay? So you have this, okay? Then the denominator is going to be the one that you're comparing it to, something like this, okay? So what happens here? You know your standard rule pretty well, okay? So if you don't remember what the standard rule is, the insides together, the outsides together, so you have that's going to be n power 5 plus 10n divided by 4n power 5 minus n power 3 plus 7, okay? So you can see here that since you compare the highest exponent of both, this limit is going to be 1 over 4. Okay, otherwise you can divide every single term by n to the power of 5 and then you would get the same thing. Or worst case scenario, you would do L'Hopital, but then you would need to justify 5 times L'Hopital and you would have the same thing. Okay, so you can see that this number is positive, okay, and finite, okay, because, okay, finite and positive. Okay, so I'm very happy because with this, we can conclude with the limit comparison test, okay? So what's your conclusion? Thus, my original, what's my original? N equals 1 to infinity of n power 4 plus 10 divided by 4 times n power 5 minus n cubed plus 7. And this one is going to diverge, okay? Diverges, okay, by limit comparison test. And that's pretty much it for this problem. Isn't that nice? So I like it, okay? I like the limit comparison test. Let's do the next one, Okay, the next one that we have over here is pretty similar to the ones that we use the direct comparison. Why would we not use and we cannot use direct comparison? Okay, so this one, like the ones that we have from the previous page, you have that you are going to compare, okay, to this beautiful series, starts at 2, infinity, 1 over n power 3. So this one is a p series, okay, and you can see that your p is equal to 3, which is greater than 1, okay. So what you can conclude here is converges, okay, by p series test, okay, so we're all happy about that, okay. But then you're like, okay, if it converges and I'm using direct, not limit, you want this one to be bigger than this one. But when you compare the denominator, what happens? That's not going to fly. So what are we going to do? The limit comparison test. That's when the limit comparison test enters to save the day. Okay? So you are like, okay, let's do limit when n approaches to infinity, and then you have your original at the top divided by the one that you are comparing it to, which in this case it's 1 over n power 3. Okay, you use your sandwich again, okay, so remember we multiply the extremes and multiply the insides, okay, so you have n power 3 divided by n power 3 minus 2, and this one again you can see that the exponents are the same, therefore you have 1, okay, it's your limit, you know that 1 is finite, and also it's a beautiful positive number, okay, which is great. Okay, therefore, what can you conclude? Therefore, okay, my original series, which starts at 2, okay, and goes to infinity, you know that this guy over here, okay, you can see that it converges, okay, by limit comparison test. And that's pretty much it for today. I hope that you find this video helpful. Bye!